Welcome back to another lecture from organic chemistry. In this lecture, I'm going to go through acid catalyzed hydration. Technically, we're going to have a double bond, and to that double bond, we will add one molecule. To one side, we'll have H, and to another side, OH will be attached to the second side of the double bond. The question is going to be where we should add the H. The addition is going to follow Markov-Nikov's selectivity, or rigid selectivity, and rigid selectivity. That means hydrogen will be added, or H plus will be added to a carbon with less substituent, while OH will be added to a carbon with more substituent. A reaction is going to be initiated by acidic condition. You need to have acid, and the one way to present it is to say we have a hydronium ion. If you write just hydronium ion top of a vector or like arrow, that means it's acidic condition. And because they wrote hydronium ion, the solvent must be water. Okay. Another way to present it is to write sulfuric acid, the top of an arrow. That means it's going to be acidic condition, but we don't want it to be really high concentration concentrated of sulfuric acid. And in order to say this is a diluted acidic condition, we write water there. So from now, anytime you see this sign H2SO4, and then it says slash H2O, that means this one is diluted solution. Okay, diluted solution. We want it to be a diluted solution. And the first step, or like the initial step of the chemical reaction, is going to be this. We have double bond. Where is the double bond? This is the double bond. Okay, next, let's assign the order of the carbon that attach to or involved in this double bond. On the left side, we have a secondary carbon. Right side, we have a tertiary carbon. Okay, next, we have acid, is hydronium ion. Our nucleophile, it will be the double bond, and the double bond is going to use these two electrons to attack technically hydronium ion, or take H plus from it. And which one of this is going to attack, which one of this carbon is going to attack water or hydronium? As I said, the one with less substituent. Okay, the one with less substituent, or the one with more hydrogen. Left side, it has one hydrogen. Right side, no hydrogen at all. We have just two methyl groups. So technically, this carbon, the one, okay, one on the left side is going to attack hydrogen, and it attack hydrogen ion, and it will take H from it. And the result, is going to be this. Okay, so we get this structure. Now we're going to have a positive charge there, okay, on carbon, and the carbon that is tertiary. And the left side, remember that from before we had H there, okay, no doubt about that one. Now we added H, new H, and then new H, I'm going to write it here. Okay, and that's the H that we got from water. Okay, so this is going to be our carbocation, or the intermediate. Okay. Intermediate, it has a carbon that is not acted, so clearly it's not going to be stable. And what's the second product? The second product, remember, you removed H from hydronium ion. So this H, the one I'm going to highlight, this H is gone. And what happened with those two electrons? Those two electrons given to oxygen. So that means we have oxygen that attached to two hydrogens. This oxygen, it has two lone pair. Now, it's time for water to get involved, and water, it can attack this carbon. Okay, of course, water can be added from both sides to that carbon. Okay, which carbon? Again, this carbon, the one I just highlighted. Okay, and if that one happened, we get such a product. Okay, so we get, okay. In OH, it will be added somewhere here. Okay. OH, it will be added to this carbon. Okay, and I'm gonna just simply say this is gonna be O, H, H, and clearly oxygen is going to have a positive charge. That's the intermediate, okay? Or you can just simply, okay, you can, forgive me, you can present it here, say O attached to two hydrogens, and it has a lone pair, so that means it's going to have a positive charge. Okay, good. Now, what's the meaning of the wavy bond? It means it can be a front or attached to back of the molecule. Okay, front or back of the molecule. And remember, front, we show it by this sign, wedge, or those, dashed line. Okay, because I can have, like if the groups are different, I can have technically stereocenter. In this case, both of them are methyl, so it's not going to change the story. Now, what will happen to this species? Okay, this is a species. Okay, it can get involved in a chemical reaction with one water molecule, and that water molecule, which is the solvent, it can attack this hydrogen, and if it attacks, we will get such a product. This is going to be our technically product. Okay, so H is gone. One of the H is gone. Now we will have oxygen attached to carbon, and oxygen, it has two lone pair, and we got what? We got hydronium ion again. Okay, so we started with hydronium ion and we got it back again. And this is going to be our alcohol. What's the name for it? Starting from here, 1, 2, 3, 4, and the name for it is going to be 2-methyl. Okay, and then say 2-methyl, we have like alcohol. Where is it? Is it on the second, the second carbon? So you can call it 2 butanol. Okay, and nol, OL stands for OH. Okay. Okay, so addition of the hydronium ion, okay, or the water in our nucleophile. So water behaved as nucleophile. The addition said it can happen from the top or bottom of the molecule. And in this case, we don't get a stereocenter. Why? Because these two substituents are identical. So we don't have a stereocenter. Okay. But what will happen if, like the two side or double side, like both sides of carbon are not identical? Those two are not identical. In that case, there is a possibility of getting a stereocenter. Okay, let's go after it. Okay, in this case, the reaction is going to start with adding H plus, okay, to where we have one carbon that it has one H, the other side it doesn't have, and this carbon is a secondary carbon, that one is tertiary carbon. So add the H to a side, to add H to a side to get the most stable carbocation. If I add H to this side, I get positive charge there. This is going to be a secondary carbocation. Okay, if I add it to the tertiary carbon, but if I add it, to a secondary carbon, okay, and put H here, remember we did have H before, okay, and if I add H here, now I will have a carbocation that is tertiary. So which one is more stable? Okay, the second one is more stable. Okay, so I'm going to add H to the secondary carbon in order to get a tertiary carbocation. Okay, this one, it will be the favored one. Okay, and after that, this intermediate will be involved in a nucleophilic attack. So next step, I'm going to say I have water. And water with two lone pairs, it will attack this carbon. The addition, it can happen from the top or bottom. Okay. And so forgive me, I forgot to draw an ethyl group here. Okay. And in that case, I get this molecule. So H was added here, and the OH we added to this carbon. So we're gonna get OH. And of course, first step is gonna be, technically it's gonna be O attached to 2 hydrogens, and then solvent will get involved. And if solvent get involved, the final product, it will be OH. So I just wrote the final product and just to speed actually the video. Okay. Now, if I go after this center, this carbon, I see 4 different substituents. So that carbon, it can be stereocenter. And yes, that carbon is the stereocenter. And let's review it. So we have this. It said if the addition happened from the bottom, we get OH attached to the bottom, or if and if this one happened from the top, so I'm gonna copy paste this one. You add OH to the top of the molecule. These two, they should have different, stereo the configuration. And okay, they should have the different configuration. Here, I cannot assign whether this is going to be R or S. The only thing I can say, if, for example, if this one, the first one, is attached back of the molecule, it should have different configuration than the OH that attached to the top of the molecule, but they will be 50%. So I will have 50% from 50% from this. Okay, from this enantiomer, and 50% from the second enantiomer. They will cancel each other, and I will not see any optical activity. Okay. Next one. Okay, I made it a ring. And because it will be easier actually to assign R and S. Okay, so the first step, we're going to have H, and H, it will be added to this carbon. Okay, this carbon. Why? Because that carbon, it has a hydrogen and is a secondary carbon, and that one is a tertiary carbon. If we add H to this carbon, we will get a tertiary carbocation. So now I got tertiary carbocation. Now what will happen in next step? Next step, water as a nucleophile gets involved, and it will attack this carbon. Okay, and that's gonna give me OH. Okay, so let's write whatever we have until now. Okay, so we have 2 hydrogens here. And the yellow carbon, it has a substituent, and what's a substituent is methyl. Okay, and in one case, I'm gonna say addition happened from the top. If the addition happened from the top, I get OH, top of the molecule, and methyl, it will go back of the molecule. Or if addition happened from the top, okay, in that case, addition happened from the bottom of the molecule. In that case, the methyl, okay, the methyl group will be facing up. So this is going to be methyl, and back of the molecule, we will have OH. Okay, now, do I have a stereocenter here? Yes, I have a stereocenter. This is my stereocenter. Okay. And so that's going to be the stereo center. And the order, I go, this is the first priority. Next priority, it will be this carbon. And this is going to be the third priority. And methyl, it will be the fourth. So what's the configuration for it? Forgive me. What's the configuration for it? 1, 2. If I follow the numbers, this is going to be R. Okay. Next one, I go 1, 2. Okay. 1, 2. Okay, this one, it will be 3. Okay, and you can put the 2 here, 2, and that's going to be 3. And rotation, okay, again, it looks is a clockwise, but because the fourth priority is facing to us, so we say it looks is R, we're going to flip it to S, so the configuration it will be S. So as you see, and hydration here is similar to hydrohalogenation, will give us 2 enantiomers, and there will be 50-50, and so we're not going to see optical activity unless one side of the molecule, because of steric effect, is blocked. Okay, that's a good story, but not for today. Okay, and I mentioned that, you know, when you are adding acid, you need to say this is diluted. Why? Because we, you know, we are dealing with equilibrium. Okay, one side, when you add water to an alkene, you get alcohol. Another reaction, the back reaction, reverse reaction, is technically dehydration of alcohol. So if you dehydrate an alcohol, you get alkene. If you hydrate of alkene, you get alcohol. In order to get alcohol, we need to dilute it. Okay, we need to have diluted acidic solution. Okay, but in order to dehydrate it, and you need to have high concentration, acidic concentration. Okay. And if you use high concentration of sulfuric acid, it will take water from it, and it will turn it to alkene. And you can actually practice this one with a piece of paper. If you take a piece of paper and drop some high concentration of sulfuric acid to it, you will see that paper, it will turn to black object, because it will lose water and it will turn just simply to carbon. And this is going to be end of the lecture, and thank you very much.